Hello friends, I Professor Darshan Thakur from Terna Engg.College, Dharashiv welcomes you on my YouTube channel for this subject here, Control System Engineering. Friends, today's objective for this session is to draw, as you can see, our objective is to, we need to draw the force voltage analogous circuit of this given mechanical system. That is our objective. Key, we need to convert this mechanical system into its electrical equivalent system by means of force voltage analogy. Right? So friends, what we need to do, this entire solution is divided into three basic steps. Right? There are three basic steps by which we can convert this mechanical system into equivalent electrical system by means of force voltage analogy. So in that first step, first of all, we need to observe from sake of observation ki how many physical mechanical elements we do have within that given system. So as far as this given system is concerned, so as you can see, this mass is denoted by M, damper is denoted by B, and spring is denoted by K. So there are three identical elements, one is mass, one is damper, and one is spring, right? So after that, immediately what we need to do, we will come to know that there are three basic elements, one is mass, one is damper B, and another is nothing but what? K, right? Then immediately after that, before converting this mechanical system into equivalent electrical system by means of force voltage analogy, before that we need to draw the nodal equivalent diagram for this given mechanical system. Means, as far as this nodal diagram is concerned, so in that nodal diagram we need to determine how many number of nodes we need to include in that nodal diagram, right? So always you need to remember that number of nodes equals to number of displacement, right? Number of nodes equals to number of displacement, right? Here in this entire mechanical system, there are how many displacements? Number of displacements equals to number of masses, right? As we are having only one mass, so this x is nothing but what? The displacement associated with this mass m, right? So in that second step, we will come to know that we need to include how many number of nodes? According to number of displacement or according to number of masses, we need to include only one node plus one dummy node, right? So number of nodes equals to 2, right? And in that third step, what we need to do, we need to draw the equivalent electrical system of this given mechanical system, right? So in this way, these are the three basic steps which involves in case of this force voltage analogous circuit, right? So in that first step, what we need to do, we will come to know that there are three elements, right? Here I will draw the nodal diagram for this given mechanical system, right? As I told you earlier, number of nodes equals to number of masses or the number of displacements. As we are having only one mass, so there will be only one node, and this bottom line represents the reference axis, or that represents the dummy node, right? This reference axis. With respect to this reference axis, this force is being applied on these three elements of this mechanical system associated with this displacement quantities as an x. So this x is denoted with this node. Let us point out that node as x, right? Now as far as this mass is concerned, it is associated with this displacement displacement x, right? Now this mass is connected in between this reference axis, right? This is how that mass is, this object is placed in this given mechanical system. It is associated with this displacement x as a result of force applied, and this applied force is with respect to this reference axis. So this mass is connected in between this displacement x and this reference axis. So this is how that mass is being shown within that nodal diagram, right? Then as far as these two remaining elements are concerned, spring and damper. So both these two elements we are having two different ends, right? And out of these two mechanical elements, the lower terminal of these two elements are kept at this reference axis, and the upper terminals are concerned, those are associated with this displacement x. Obviously, this upper terminal is connected to this displacement x, this upper terminal is connected to displacement x, or it is associated with this displacement x, and these lower terminals are concerned, these lower terminals are connected to reference axis. So in this way, we need to connect these two elements into this nodal diagram. Key, the spring is connected in between this x and reference axis like this. Similarly, this damper is being connected in between this x and this is reference axis, right? Then what about this force, right? The direction of force and the direction of displacements are similar to each other. So as this is the node, so to this node this force is being applied, right, which is shown with this symbol. This is nothing but what? The direction of applied force. So this is the first step, which involves, in case of this objective, in which we are supposed to draw the equivalent electrical network for this given mechanical system, in which we need to, or we had included one node which represents this displacement x associated with this mass m. Number of masses equals to number of nodes, and number of nodes equals to number of displacements. As we are having only one displacement, so there will be only one main node, and this is nothing but what? The dummy node or the reference node, right? So these elements are associated with this displacement x and the dummy node or the reference axis. So in this way, this k, m and this b, these three elements are being connected into this nodal diagram, and this will be the direction of applied force, right? Then after that, in that second step, this is first step, as we are having this node with us, so at this node we need to apply the Kirchhoff current law in terms of forces, right? This Kirchhoff current law, most of the time it is being applied at this particular junction or the node of that network where the multiple number of branches are interconnected with each other, right? So according to this Kirchhoff current law, which says that summation of incoming plus outgoing currents are equals to 0, or summation of incoming currents are equals to summation of outgoing currents, right? So we need to observe that at that particular node there are how many branches which are being interconnected? 1, 2, 3 and 4. Out of that 4 branches, the nature of this F is incoming towards that particular node, right? As far as these 3 elements are concerned, so the forces belongs to these 3 elements are outgoing. Such type of assumption we need to do. Out of that 4 element, this the force, the direction of applied force is incoming towards this node denoted by this displacement x, right? As far as these 3 remaining elements are concerned, so the forces belongs to these 3 elements are outgoing from that node. So accordingly, when we write the KCL equation in terms of force, so it will become capital F, right? We need to recall the system equation for the spring. The spring is associated with this displacement x, so it will become kx plus, because KCL is nothing but what? The sum of summation of incoming currents equals to summation of outgoing currents. In terms of forces, the sum of incoming forces equals to summation of outgoing forces. So there will be only one incoming force and there are 3 outgoing forces. Out of that 3 forces, the force equation for spring, according to its basic definition, it will be K into X plus. As far as the spring is concerned, so we need to recall the force equation for this mass. So it will become m into d square upon dt square followed by this displacement x, right? So it will become d square x upon dt square. As far as this damper or the frictional element is concerned, so the force equation will be what? D by dt followed by displacement. As the lower end of this damper is associated with this dummy node whose displacement is exactly equals to 0, and the upper terminal is associated with this displacement x. So as a result of this, its force equation will become what? B into dx by dt, right? So when we consider, if suppose this is equation number 1, right? This is nothing but what? Equation number 1. Then after that, what we need to do according to the force voltage analogy, because we need to apply the force voltage analogy to convert this mechanical system into electrical system. According to force voltage analogy, this M is analogous to L, right? Then this B is analogous to R, this K is analogous to 1 over C, and this X is analogous to Q, right? So when we replace this term with this analogous term, so F is analogous to V, K is analogous to C, X is analogous to Q, plus M is analogous to L. Again it will become D square Q upon dt square, plus B is analogous to R. It will become dq by dt, right? Then after that, when we apply the Laplace transform to this existing statement, it will become what? V of s equals to 1 over c into q of s, plus, as we are having the second order differentiation, so it will become s square into q of s, plus r into first order differentiation, means Laplace variable will be s, rs into q of s, right? Then after that, we need to replace this quantity I of s equals to what? S into q of s, because in that force voltage analogy, I is replaced with this dq by dt. When we apply Laplace transform, so it will become I of s into s into q of s, right? So when we replace this I of s with the subsequent term, so this upper equation, above equation will become V of s equals to, as we don't have s term, so it will become 1 over cs into I of s, plus we are having ls square into q of s, so it will become ls into I of s, plus s into q of s is being replaced by I of s, so it will become r into I of s. When we are treating this equation, and when I am putting this equation in this rectangular box, then you just carefully try to see the coefficients of this electrical element. The coefficient of this 1 over c is nothing but what? I of s. The coefficient of L is nothing but what? I of s. The coefficient of R is nothing but what? I of s. And which mathematical sign we used to have in between these three electrical elements? This plus, right? Means this is nothing but what? The ohmic drop. This is also ohmic drop, and this is nothing but what? The ohmic drop. The similar current flow through this R, L, and 1 over C. So accordingly, the equivalent electrical network will be what? This is nothing but what? The first element R. This is nothing but second element L, and this is nothing but what? Third element C, right? And which voltage is being applied here? V of s. So this is plus minus V of s, and which current flow through this C, L, and R? I of s, I of s, and I of s. So that is nothing but what? I of s. So this is R, this is L, and this is C. So this is nothing but what? Our final answer. The equivalent electrical circuit for this given mechanical system by using this force voltage analogy. In that force voltage analogy, this mass is analogous to L, B is analogous to R, K is analogous to elasticity 1 over C, and this displacement is analogous to charge, right? So this is how that given mechanical system is converted into the electrical equivalent system by the virtue of this force voltage analogy. Thank you.